Welcome in dark core. See this structure? Looks scary and devoid of any possibility of life. But this is our home, the Earth at the beginning of its existence, 4.6 billion years ago. And its formation and the formation of the Moon remain a mystery. But today, we will tell you about the theories that scientists suggested. You will learn how planets so different from each other form from the same material, what planet crashed into the Earth in the past, how much water there is on our planet, and where it came from. And finally, we will tell you how old the oldest organism on Earth is. We prepared the story of our planet, from a clump of dust and gas a few miles in diameter to the appearance of life. Plus, INTRO, when the Sun was created, gases and other materials around it started colliding with each other and forming small bodies, called planetesimals. And as the gravitational forces were growing, more material was pulled together and these seeds of planets grew larger until they became true planets. The solar system's gas giants, Jupiter and Saturn, Uranus and Neptune, were born much earlier than the four known terrestrial planets, Mercury, Venus, Earth, and Mars. 1, 2. But how exactly was our home planet born? Plus, Earth birth. The Earth's story started about 4.6 billion years ago in a disc-shaped cloud of dust and gas rotating around the early Sun. And we know it was that long ago because of the fossil record, one of the most simple methods to determine the age of our planet. 3, 6, 7. Scientists were able to find zircon crystals that are roughly 4.3 billion years old. So far, these crystals are the oldest materials found on our planet. 8. But how exactly our planet was formed remains a scientific mystery. However, there are two leading theories on planetary formation. The core accretion model is the first one and most widely accepted. About 4.6 billion years ago, there was a solar nebula consisting of spinning gas and dust particles from which our Sun was born. Then, as the remaining material of different sizes orbited our star at slightly different speeds, it started to collide and stick together. Under the effect of gravity, smaller particles grew into larger particles that ranged from miles to hundreds of miles in diameter. The solar wind would then sweep away lighter elements, such as hydrogen and helium, so that just rocky materials would stay closer and turn into terrestrial worlds. The process continues until these space objects reach thousands of miles in diameter. But far away from the star, the Sun's constant stream of charged particles doesn't have a very strong impact on lighter elements. As a result, these elements combine and transform into gas giants. 1, 3. What's exciting is that NASA believes that if this is the way planetary formation works, small, rocky worlds like the Earth are a lot more common throughout the universe than gas giants. The thing with this theory is that it works well to explain the formation of terrestrial planets but has problems explaining the creation of giant worlds. This is because scientists believe the gas disk around our Sun only lasted about 4 to 5 million years. And simulations based on the core accretion model show such planets form longer than that. 1, 5. However, the second theory or the disk instability model resolves this issue. This newer idea suggests that chunks of dust and gas clump together early in the existence of the solar system. And, over time, these chunks slowly turn into a giant planet. But the difference is that this way, planets can form much faster than those explained by the core accretion model. In fact, according to this theory, it could happen within as little as 1,000 years. A planetary formation this fast makes it possible for such worlds to trap the rapidly vanishing lighter gases. 1, 5. A recent study suggests that proto-Earth was formed within about 5 million years. And, on a cosmic scale, it's nothing. If we converted the solar system's estimated 4.6 billion years of existence into a 24-hour period, these 5 million years would be equal to just about 1.5 minutes. 4. If scientists are right about this, water could be just a byproduct of the formation of a planet similar to our home. This would mean that we're a lot more likely to discover the ingredients for life outside our solar system. 4. And what about our satellite? What's the story of the Moon? Plus, moon formation. Astronomers have proposed many hypotheses for the origin of our satellite. And some of them are quite bizarre. 10. The fission theory suggests that the Moon was once a part of our planet. When the Earth was still a hot ball of spinning lava, it may have ejected the material our satellite is made of now. While most scientists remain skeptical because of how fast our planet must have been spinning to make this happen, it would have been a breathtaking phenomenon to observe. 13. The capture theory is yet another interesting idea suggesting that the Moon could have been captured from a different part of the solar system. We already know that some worlds have gained their moons in such a way. Perhaps, before it was attracted by our planet's gravitational pull, the Moon was orbiting Venus. Still, this wouldn't answer the question of why the Earth and the Moon have almost identical oxygen and isotope ratios. But the next theory could. 10. 11. Some astronomers think our satellite was created side by side with Earth. The idea is that both were formed at about the same time, from the same gas and dust, and at the same part of our solar system's protoplanetary disk. The theory is called coformation and it fits because of the isotopic similarities between the two space objects. But at the same time, it cannot explain the difference in the size of their iron cores. 11. The leading and, perhaps, the most mind-blowing theory is that the Moon was born as a result of a giant impact with a different celestial body. There's a chance that Earth wasn't the only planet that was forming 150 million kilometers, 93 million miles, from the Sun. Earth's creation may have been accompanied by another planet dubbed Theia. This strange world must have been smaller than our planet, just about the size and mass of Mars. At first, it could have a stable orbit, but as Earth increased its mass by gathering more material, Theia's orbit was destabilized. And so it swung back and forth toward our planet until, eventually, the two protoplanets collided. The speed of collision was low, so the Earth wasn't destroyed. However, the impact must have created a disk of debris of molten rock and hot gas that became the building blocks of the Moon. Both Theia and the Earth could be composed of a combination of materials, and more of the lower density splatter would eventually transform into the Moon. If this is the case, it explains why our planet has a higher density and thicker core than our satellite, and why the Earth and the Moon spin the way they do around each other. 10, 11, 12, 14, but let's get back to Earth. Throughout the next 500 million years, Hadean eon 4.5 to 4.0 billion years ago, the Earth resembled a ball of a molten surface, volcanism, and asteroid impacts. And several things made it extremely hot: gravitational compression, radioactive decay, and asteroid impacts. A big amount of this initial heat is still there, deep inside our planet. But as it cooled, minerals started to crystallize, and because of the different densities of materials, the crust, mantle, and core were formed. 9. So how did water appear on a hot rock floating through space? Plus, origin of water, oceans cover more than 70% of the Earth's surface. This is 1.386 billion cubic kilometers, 333 million cubic miles, of surface water or ice. 17, 18, but the fact that there's more liquid water on our planet than on any other known rocky world in our solar system isn't fully understood. And as with the Earth and the Moon, there are several hypotheses as to how water appeared here. One likely reason is extraplanetary sources, such as comets, trans-Neptunian objects, or even protoplanets. There's actually a lot of water in our solar system. 2/3 of Uranus and Neptune, for example, are made of ice. 20. So if our planet was born hot and dry, then water must have come from somewhere else, brought by icy comets and asteroids. Comets are made of dust and ice, with most of that ice being frozen water. So they might be the clue. But measurements show that comet water has a lot more deuterium in it compared to that found on Earth. What about asteroids? Because their ratio of deuterium to normal hydrogen water is closer to that we have on our planet, they are even a better candidate. Also, asteroids are 20% water, but due to their small size, there must have been a colossal number of impacts to explain all the water on our planet. To fill the planet with 1,386 million cubic kilometers of water might seem like a lot. To compare, this much water would have been enough to cover the contiguous United States to a depth of roughly 145 kilometers, 107 miles. But this still isn't a lot. In fact, water amounts to only about 0.02% of our planet's mass. And since Earth experienced periods of heavy bombardment in the past, this is actually a possible scenario. 10, 19, 21, 22. Researchers also think that when our planet formed, huge amounts of hydrogen were captured in its rocks and minerals. And because of the mantle's heat, hydrogen and oxygen-rich minerals started to melt. This made it possible for water to spew from the Earth's crust. According to scientists' estimates, about 10 oceans of water could exist within the mantle up to this date. 23. Probably the most astonishing of all is the volcanic outgassing hypothesis. According to this idea, water may have come from volcanism. In other words, it was always there in the form of minerals with oxygen and hydrogen, hidden beneath the crust of our planet. And volcanoes only helped it break free as vapor. It originated in volcanic eruptions, then condensed and fell as rain. Scientists think that all volcanic eruptions contain some water vapor, and that it may have been enough to account for the Earth's surface water. 15. 16. This still remains an open question, but whatever the case, with water, there often comes life. Plus, first life, most likely, began during the late Hadean or early Archean eon that lasted from 4.0 to 2.5 billion years ago. There's evidence of life in at least 3.8 billion-year-old rocks from Achilea Island, Greenland, and the oldest form of life discovered by scientists are tiny hematite tubes estimated to be 4.28 billion years old. 10, 24, 25, 26 hypotheses include a chemical origin of life in the early atmosphere, hydrothermal vents, deep seas, oceans, and even comets that came here from somewhere in space. 10. It's highly possible that life began from the chemical environment of the early atmosphere and oceans. But they were nothing like what we have today. The atmosphere was oxygen-free but was abundant in methane, carbon dioxide, sulfur, and nitrogen compounds. And some space objects in our solar system are known to have an atmosphere like this. In one experiment, scientists simulated our planet's early atmosphere and lightning within a sealed vessel. They found that after igniting sparks, amino acids or the fundamental building blocks of proteins were formed. 10. Life that could have started on the deep ocean floor may have also been able to survive without photosynthesis due to another biological process called chemosynthesis. Instead of using the energy of the sun, primitive life gained energy from the heat that was coming from the Earth's interior. 10. Still, there's always a possibility that life initially originated in space and was then carried here by comets or other celestial bodies. Researchers have already found amino acids within meteorites and comets. What's exciting about this idea is that it means a high likelihood of life existing elsewhere in space. 10. We hope you enjoyed our story of the formation of Earth and its satellite, the origin of water, and primitive life. But if you'd like to hear about multicellular organisms and how intelligent life evolved, let us know in the comments. Thanks for watching Dark Core.